All right. Well, we'll get started. My name is Tony Petrosian. I work in the database engineering team at AWS. I have my friend Ian here. He's going to join us later. And we're going to talk about databases and which database to use when. It's a loaded question. We've got a lot of loaded answers for you. So one of the things we're not going to start with is we're not going to start with these generalities. So we're not going to say, well, if you need relational or non-relational or SQL, no SQL. We're just going to dive into some more detailed stuff. The idea is that most databases that were ever developed, built, invented, were built for a purpose. And when you find a database which was built for the purpose and that your application really needs that stuff, then you have the best match. So when your application needs meet the purposes of the database when it was invented, you have a good match. So this being a database conversation and it's being about storing, retrieving, and processing data, let's take a look at the data first. So usually the things that I look at when looking at databases and which database to use in the application, I look at the application with respect to the data and the shape of the data and the size of the data and the computational requirements for that data. And these are really three important things that help you decide which database is the right database for your application. So we'll spend some time talking about these three things, and then we'll dive into more details. So, shape. When it comes to databases, relational databases have been around a long time, since the 70s. And they were built around the row. So the concept of a row is a fundamental component of an RDBMS. If you go read the papers from the 70s, they talk about the tuple, which is the row, and row has many columns. But row stores are generally built and optimized for doing things at the row level. So the smallest unit of operation is a row. You get the row, you update the row, you delete the row, you insert the row. And most of the stuff is, based on that. So then you have your records, which in the form of a row and a group of rows. Most applications that were built for payroll and HR and finance and so on modeled the data in form of rows, which was great. And it had good performance. When you wanted to basically deal with a record, like a new employee joins, you create a record for it, and the record fits in this row, and all the columns are there, and you operate at the row. And then years goes by, and people have lots of data in their databases, and they're doing queries. Now people want to do sums and aggregations to figure out how much stuff did we sell last month, or last 3 months, or last year, or last quarter. So you start doing a lot of query processing. And one of the interesting things about query processing is that you usually don't run a query that requires the entire row. Because, for example, you're looking at the sales figures. So you want a sum of all the sales. Or you want to do sum of all the salaries, or something like that. Maybe you need 2 columns or 3 columns. So doing the analytics workloads on row store became expensive and inefficient. So that's why column store was invented. And column store stores the data in form of a column. It takes the row, it breaks it up, and it stores each column separately. And this gives you great performance and efficiency when you're doing a query which goes out and gets 10 million or 1 billion rows, but only interested in the one column which has the sales figures, and you're doing a sum or a min or a max. So you only work at the subset of the data that you need. And that's why when you do aggregations, scans, joins, columnar databases work really well. And then we have key value stores. And it gets a little simpler because key value stores were invented to store keys and values, where you are doing queries based on a key. Right? And the idea was, I need to do a lot of key value lookups, and I need them to be really, really fast. And I want them to be always fast, regardless of the size of the data. And that's one of the reasons key value stores are used in so many workloads, where you have vast amounts of partitionable data, where you need, I need every time I go get a value using a key, I need that to happen in 3 milliseconds. Whether I have 1 billion or 100 billion or 1 trillion items in my table, I need that consistent performance. Document stores were invented to hold guess what? Documents. There's a lot of data which fits really nicely in the form of a document. So for example, if you're building an application to keep track of patient records, well, a patient doesn't fit in a row. You know, every time you go to the doctors, they take notes and stuff. That's a lot of data is generated. It doesn't really lend itself to the row format. So trying to define a person and their medical history in rows is just not efficient. Whereas you can say a patient is a collection of documents, and we add to the document another document every time you go see the doctor. So it becomes an easy way of modeling things, which is a document. So document stores are invented for that. They're really good for storing documents, indexing, and storing documents, querying documents on various properties of the document. Graph store, well, when you need to persist relationships, graph store is a really good thing. Now, a lot of people say, well, relational databases should be really good for relations, right? And the answer is, well, no, graph is not really a relation. Graph is a graph. And so the interesting thing about graph store is that it actually persists the relationship so that it's really fast at retrieving and processing relationship data. So social graphs, recommendation, things like that fits really well in a graph store. And then time series is, of course, is the data which is sequenced in time. You almost never update it. It's always an insert workload. And what is a good time series data? Stock data. What was the price of particular stock at a particular second during the day? And you have one of these records every second, forever, right? And then you usually look at time series data, not based on a particular point in time, but usually a set of computation applied to a range of data. Like, what was the min, max, and average CPU utilization for my database servers in the last 3 days? Right? So you go get the range of data, you apply the computation, and you return the answer. So the job of a time series store is to return answers, not give you the data so you can go compute it later. An unstructured store is exactly that. It's for storing unstructured data, where you impose the structure on the data yourself. Size. The interesting thing about size is that the size at limit is far more interesting than the current size of your database. And what do we mean by size at limit? There are some workloads that generate data where the size of the data is fairly well bounded. For example, if you build an app to track employees of a company, you say, well, we have 10,000 employees, we have aspirations to grow and have 100,000 employees. Okay, so you're going to have 10x more data, 100,000. You're not going to go and hire every person on the planet, right? So the size of the data is fairly well bounded. As opposed to something like, I'm going to keep track of sensors in a particular car. And cars used to have 10, 12 sensors 40 years ago. Now they have thousands of sensors. And probably self-driving cars will have tens of thousands or hundreds of thousands of sensors per car. It is an unbounded problem. You have no idea how big it's going to be, but it'll probably be big. And so that is a really important element when picking databases. And working set size and retrieval size, partitioning versus non-partitioning. There's some workloads that lend themselves really well for being partitionable because you store the data based on certain partitioning keys, and you compute the data based on the same partitioning keys. And a good example is like the location of a car. The location of my car, wherever it is, has nothing to do with the location of your car. So it's a nicely partitionable thing. Each data element is its own thing. As opposed to the payroll data is not really partitionable because you kind of look at an employee or group of employees or all the employees, so you can be able to apply processing to all of it. So take these things into consideration. And then there's compute. When it comes to compute, we have stores that are really, really good at retrieving data and storing data. But they don't do a lot of computation for it, right? So that's not their job. They're get, put, but do it really, really fast. I want you to go and get the rows that match a particular predicate, filter it, sort it, right? That's very different than saying, go calculate the sum of these 10 billion rows, a particular column, and give me the answer. Where you are perhaps processing a terabyte of data and coming out with the answer 7, versus in the other case where you're basically saying, give me the row, give me the row, give me the item, give me the document, right? Throughput, latency, change rate, rate of ingestion, these are all things that you have to consider when choosing a database. For example, if you are picking a database to keep track of the location of cars every minute, then you get a lot of inserts, because there's a lot of cars on this planet. And I don't know, maybe the particular brand of car you're selling, there's tens of millions of them out there. And you want to record their location every minute when they're changing. Well, that's a lot of data to ingest. As opposed to keeping track of employees. Maybe you hire 10 employees a month. I don't know, maybe 100 employees a month. Maybe 1,000 employees a month. It's still very small compared to the location of 5 million cars every minute. OK, so shape, size, and compute. When you take into those consideration, and then you go pick a database, you go, OK, my database, my favorite database, can do it all. It's an idea that exists out there. And sometimes it's true. If you have a very small workload and not a lot of data, maybe you have, I don't know, 50 gigabytes of data, you can probably use any database, relational or whatever, any brand of database you want. And on a modern machine, the whole thing will fit in memory. The performance will be fine. That's OK. But what is the efficiency at scale that really matters? So I'm not suggesting for every workload you go find a specialized database, because there are some databases that you can generically use. But when stuff gets big, when cost is important, when operational efficiency is important, when you're dealing with 100 terabytes of data as opposed to 5 gigabytes of data, then the choice becomes really, really important. So which database to use when? Well, before we can answer that, there's this other thing that we need to talk about, which is managed database services versus unmanaged database services. And why does this matter? It matters because it changes the cost and TCO and convenience and developer capabilities. Why? If you were going to build an application 30 years ago on premises, you would go buy an enterprise class server, you would go buy some database, you would pay for the licenses per CPU core or whatever, you would hire a DBA and a system administrator, and that machine would be taken care of really well managed, the backups are always done, and so on. And the developers come and say, I need a database. You go, put it in this one because it's well maintained, right? So the developer says, OK, I've got videos, I'm going to put it in the database. I've got invoice images, I'm going to put it in the database. I've got data, row, logs, history, everything goes in the database. Why? Because it's the most convenient thing to do, because nobody wanted to go buy 10 servers, 10 different software packages, 10 different DBAs. So you try to standardize on one thing. But when you move to the cloud and you start using managed databases, a lot of those inconveniences go away. So everything is just at an end of an API call. So whether you make an API call to put an image in S3, a blob store, or you make an API call to insert a JSON item into DynamoDB, or you do an insert into a Postgres database like Aurora, it's just an API call. It's not like you have to go manage those servers and do backups on them and fix the memory when they break and replace the disks that die. So developers now have the choice of using the right set of APIs to build an application. And what this leads to is most of the modern applications that we see people building use a multitude of databases. So really, which databases to use for what components of your application? You take this one step further into, I'm building microservices. And I have a microservice for shopping cart because I'm building a retail website. Well, maybe the shopping cart stuff goes into one database. Then you do the transaction when you actually sold something, that goes into something. And then you have the recommendation, maybe that goes into graph. So it becomes a lot more convenient to use them all. So for us at AWS, the strategy is to purpose-built databases to satisfy the particular workload for the best performance, price, convenience, and programmability, without having to tell the developer, I know that you want to use different databases, but you should just pick one and stick with it because it's easier. At the end of the day, it's not easier, because you have this mismatched workloads and mismatched databases. So back to some generalities. Most workloads we look at, you can kind of split them between analytics and operational, whereas analytics data workloads are about getting insight. It may be retrospective, as in how much stuff did we sell last quarter, last year, last 5 years. You look at history. It could be streaming. It's like the data coming in from some devices, and you need to raise an alarm when something gets too hot or too cold or whatever. And there's the predictive stuff, where you look at a body of data and you try to figure out what's going to happen tomorrow, which is very different than retrospective stuff, which was what happened yesterday. Now, why is the predictive stuff important? Because most applications are now starting to employ some kind of an ML, machine learning algorithms to improve. Like, I don't know, is it going to rain tomorrow? Well, you probably have to go look at the history of the weather data and the current condition, and maybe you'll guess if it's going to rain tomorrow. Or how many people should you have employed tomorrow at the Starbucks downstairs, because there's 42,000 people running around, right? It would be good if they could predict some of that stuff better. On the operational side, you have your transactional workloads. I took $5 out of my account, took $5 out of my account, put $10 in my account. There's a system of record. Where is Tony's car? Where are the employee records? Where's this patient record? And there's content management stuff. I don't know, I spin up a blog, use WordPress. There's probably a MySQL database somewhere there, right? So let's talk about operational stuff. There's some basic characteristics that goes with operational databases. Usually a good fit for caching. Compute size is usually small, like you're dealing with 1 patient, 5 patients. A doctor can see so many patients a day. They generally require low latency. Nobody's willing for their transaction on their credit card to take 1 second. That needs to happen really, really fast. High throughput, because there's a lot of people trying to do a lot of little things. High concurrency. I don't know, there's 10 million cars. Where are they? They're all emitting telemetry, saying where they are, and you need to insert them. And there's a lot of them at the same time. And then almost all of operational data now have this mission-critical HA, DR, data protection, don't lose the stuff, backups. And then the stuff which is, useful to think about when you're making decisions are size at the limit. Is it bounded or unbounded? Are you going to deal with rows? Are you going to model your data in form of rows or key values or documents? Is it a graph? Do you need relational capabilities? Do you need to be able to push compute to the database, or do you need the database to just give you the data so you can go do whatever it is that you need to do in your application? What is the change velocity? So for example, the telemetry coming from a car, it never changes. Nobody goes back and says, no, Tony's car wasn't parked here, it was parked there, right? It's an insert-only workload. As opposed to Tony's salary is continuously updated and increased because I'm really good. Or I like to think that. So that's an update workload. It doesn't happen. It rarely gets updated. And then the ingestion requirement, again, is the ability to take in the data. So I'm going to ask Ian to come up so we can actually have a debate about what databases to use. But this is a good summary kind of way of thinking about it. Relational databases are really good if you need referential integrity, if you need strong consistency, if you need to do transactions across 5 tables, right? Key value, low latency, key-based get and put, high throughput, partitionable, unbounded data size. Documents, really good for documents. And anything that you model, like I have a 17 deep JSON document. OK, that's probably a good document. for a document store. And then there's graph. So Ian and I work together at AWS. And so we're going to talk about some. By the way, most of the slides were made by Ian. So if they're good, it's his work. So we've got Amazon RDS. We're not going to go through and explain what Amazon RDS is and what are the various databases, because chances are if you're interested in databases, you probably heard of them. But if you haven't, you can go to the website and see all of the stuff about Amazon RDS. But we do have a lot of engines. So tell me, what would be a good workload for, say, Postgres? And why would I pick Postgres versus something else?
Sure. So RDS is a great general purpose database that has the ability to start very small and then grow with your business and offer all these different engines. And so we see RDS being a great place to start for when you're building an application where you want to use common frameworks like Ruby on Rails or Django. And you may have a particular engine that you choose on the basis of skills in your teams, types of frameworks that you happen to be using, maybe third-party packages that you're bringing in from the outside. And so you can really tailor it knowing that the underlying principle of these applications are the things that we've touched on with row stores, where the database is going to validate some data for you. It's going to help you manage uniqueness constraints. It's going to allow you to push computation down to the application rather than having to write it within your code. You're going to have a database-centric compute model.
So if I have some workload on premises, I don't know, maybe I built an app and I don't want to touch the app, but the hardware is getting old and it's starting to not be so available anymore. Maybe it was written with Entity Framework. What do you have? What would you recommend? Do I rewrite it, put it in Aurora? Do I put it in Dynamo? What do I do?
Sure, yeah, so bringing applications into the cloud, certainly we see most commonly that people will start with RDS. And the reason is that they can tailor the database and the engine that you choose to exactly these sorts of requirements. So we have a SQL Server option for when you're bringing in an IIS or .NET application. And so it is very, very common that what you're looking at achieving with this kind of operational database is looking to get out of the business of doing so much management, so that maybe you can focus your time on making that application better. So you don't want to do backups, and you don't want to do patching, and you don't want to do all the hard work of running a database. So you say, look, I know it's compatible, and that allows me just to focus on my business.
Right. Now, I've got developers. They have their preferences with respect to languages. I know a lot of people love to write code in Python, use Django. What do you have for them? I'm going to build some application to keep track of, surveys in my company. Mm-hmm. Right? It's not going to get very big, but it's important stuff.
Sure. Yeah, so again, one of the reasons that you would choose one of these particular engines is going to be about the skills that you have in-house. So for instance, we see a lot of affinity between the Python community and Postgres, whereas as Tony, you said, a content management system will often have a MySQL disposition just because that's what's been used in the past. You may have an application that you're running on premises that runs on Oracle. You just want to be able to bring that in. So it really is about focusing on what your teams can do, what's going to help you be most productive, and then the nice thing about this type of service is it cuts across all of those different engine considerations and just gives you really simple to operate database.
So then tell me, what is the difference between Postgres running in RDS and Postgres running in EC2 and Postgres running as part of Amazon Aurora?
Sure. So when you pick an engine, certainly you can choose from different types of storage. That would be the contrast between using Aurora storage for Postgres versus the standard RDS Postgres, which uses EBS-based storage. But the real difference is that you're not going to focus on managing the database yourself. You're not going to think about patching the server. You're not going to think about doing backups yourself. And then really thinking about the difference between storage in Aurora or not is going to be about what are your availability characteristics? How quickly do you need to do failover? And certainly Aurora is a fantastic storage environment because it's always multi-AZ. That's a real differentiator for these types of engines. Traditional relational databases, they work with a primary node that takes responsibility for all the writes. And then in RDS, you can spin up read replicas for certain engines. Right. And as we heard, obviously, we now are going to support multi-master for where you have very, very high availability requirements.
So for massive scale relational workloads, which can get pretty big, and I'm writing an app from scratch, so I don't have preferences. I'm not using anything on-prem.
Yeah.
What would be the go-to place if I need relational capabilities?
Yeah, so Aurora every time, and then choose which engine to use on the basis of the features of your application that you're building. So a very common request is, I'm building an application that's going to have some ability to track location. And so we'll see people gravitate towards Postgres because it has PostGIS, the ability to run geospatial queries in a relational context. In other cases, you may say, again, my team is really comfortable with MySQL, but I need that massive scale. I need the ability to scale up dynamically on my storage volume, and I need it to give me a huge number of read and write IOPS. So in both cases, Aurora is a great place to start. It allows you to scale to extremely high scale over time.
So relational workloads, I need relational capabilities. I like SQL as a language. I use Java or whatever. You have a variety of things to say. But, I mean, there is a limit.
There is.
Like, if I want to record the location of every car every minute and have a massive input coming in.
Yep. Yeah, exactly. So RDS is one of these systems that we talked about. It's bounded at limit. You're going to provision a certain amount of storage, and you're going to grow into that storage, certainly with Aurora, and you're going to be flexible. But ultimately, there is a size to the database where some of the principles you mentioned, like the ability to have completely predictable performance regardless of the size of the database, where we may need to look at something that's a little bit more sophisticated and gives us some features that relational databases traditionally haven't been able to support.
All right. So
Dynamo. Yeah, so DynamoDB then is going to give us the ability to really break out of the boundaries that we may find from a relational database with the relational validation that's occurring within the database, and really gives us the ability to operate much more efficiently with unbounded scale.
Okay. Is it one or the other?
No. In fact, you'll certainly need to look at what kind of data sets really do act like unbounded at scale, and choose the right database for the kinds of requirements. So if you have a huge amount of push-down computation, you may put that against the data that sits in an RDS database. And then for certain types of things, the example you used with a shopping cart is a fantastic one. Putting your shopping cart and the ability to transact with really high availability, really high throughput, where you'll never run out of capacity, that's what makes your business successful. You put that on DynamoDB. Maybe the customer records stay in a relational database so that you can do fast mutation and validate that their addresses are correct and these sorts of things.
Right. So that's a good breakdown. I mean, I was talking to a customer earlier, and they were telling me that they have a bunch of data, and it's relational, and they put it in Postgres, but they have some massive read requirements, and it needs to be global because they're a global company, and they need it everywhere, and they need it to be synced. So they were telling me that they basically read from RDS, Postgres, and then they stuff it in Dynamo, and then they scale the reads off of Dynamo for computed results that comes from Postgres. So being able to mix and match, easy?
Yep. Absolutely, absolutely. So as soon as you want to try and scale relational data sets in the way that you're describing, for instance, using things like globally replicated Dynamo tables, then you do have to think about that in a similar way as you would think about caching, for example, where you're going to take, your application takes the responsibility of pulling the data out of an operational store that's good at storing those data elements long term, and then moving them into DynamoDB, managing the consistency between those two systems. So it is something you need to work with, but it is then very trivial to scale that working set to virtually unlimited size and presence around the globe.
So if I end up using a couple of different engines, but I need the data to easily move between them, what are the options?
Sure. So moving data between data sources is something that the data migration service is particularly good at. And then you may also be looking at the ability to use things like DynamoDB update streams. Update streams allows you to kind of listen to changes that are occurring on your Dynamo environment and then replicate those down into a relational database, for example. So there are absolutely integration patterns that allow you to move data in and out of these different environments without having to do a lot of ops.
Can you trigger like a Lambda function with these update streams to do stuff?
Yeah, absolutely. So that's one of the native integrations for DynamoDB update streams. You can run computation on the basis of an update event coming out of DynamoDB, and then do something useful with that. So that could be an example of moving data into cold storage on a different database, implementing replication, for example.
Cool. So We have this thing called DAX for DynamoDB caching. Just give me a 15-second story on caching.
Sure. So we talk about DynamoDB being able to be running with scale that's unbounded. DAX really then gives us virtually unbounded low latency. So what DAX allows us to do, we create a layer with DynamoDB, or we implement our application on DynamoDB so that we get really high availability and really high performance. But we can also now add DAX, which drives the latency down to microseconds, but where we don't have to worry about managing the complexity of cache management, where we don't have to think about, well, is the data up to date in my DynamoDB table versus my cache? And the reason is that DAX is what we call a write-through cache. So I just do the writes to DAX, and DAX takes responsibility for writing to DynamoDB. So I get all the benefits. I get API compliance with DynamoDB, but I get this massive acceleration in performance. A really nice thing to have where you want to have microsecond performance.
What about Elasticache? When do I use that?
Sure. So Elasticache,
database workload thing?
Yeah, so Elasticache is then where you want to add caching on, but you're using a different type of operational store. And the real difference between something like DAX being a write-through cache and Elasticache where you're adding it on to one of these other operational systems is that your application is going to take responsibility for making the cache and the data store consistent. And there are lots of frameworks that will do this for you. We talked about the choice of RDS, very general purpose database, because you might be using some type of an entity management framework. Well, very consistently, those entity management frameworks will allow you to plug in a cache on the side, and they'll do all the hard work of keeping that cache up to date, really fast response times. So Elasticache gives you Memcache and Redis interfaces, so you can have an open approach to bringing in your entity management frameworks, use a standard engine, but we do the hard work of operating it.
So low latency reads I need from Dynamo, I can use DAX. DAX is a specialized caching for Dynamo.
That's it.
And then Elasticache is a generic caching mechanism with Redis, and you can front that in any of the RDS databases. You probably put it in front of Dynamo as well if you really want to.
Absolutely.
So,
Absolutely.
All right, so if you need low latency reads and your data set size that you're operating in fits in the cache, then caching is a good thing. If your data is bigger than a cache and every access is a cache miss, then you're just wasting your time missing on the cache.
Right.
So there are some intricacies, so not everything is cacheable, obviously, and you have to be careful about that. All right, so we announced Neptune because we have recognized the fact that graph is really an important thing, and maybe it was, I don't know, Facebook uses graph databases because, that's a pretty big graph.
So, why would you do this? Why would you use a purpose-built and specialized database for something like relations? Is because it's actually really hard to manage graphs and relations in any other type of operational store. We have some other analytical systems that support graphs like Elasticsearch, but with the kind of performance that you're going to get from Neptune, you really do need a specially built database for that. And as you mentioned in the intro, things like making recommendations to be able to answer a question of what pieces of content are similar to a piece of content that I just said I liked. Well, I have to have a relationship between those two, and it's probably going to be a similarity. Or when I want to answer a question like, people who bought what you just bought, they also bought these other things. Well, that requires the ability to create links between people and behavior, and then those relations themselves actually have traits. They have properties that are interesting and meaningful. And modeling data in that way in a relational database is really complicated. Yeah. Modeling it that way in DynamoDB, you can absolutely do, but graph databases are specialized for then querying that data. And there are specific algorithms for graph that are really important.
I recently got a lecture on this because I was saying, I can model relations in a relational database and write queries. And then somebody showed me the SQL text of computing the relationships between family members and the graph version, like in Gremlin, which is like a one-line statement. And so the idea is that, it's really difficult when you have to compute the relationships between, say, myself and every family member in a relational, because you have to compute that relation at the time of query, as opposed to using something like a graph store where the relationship is persisted. And so you just get the relationship and you can walk the nodes. So
quick show of hands in the audience. Has anybody in here ever written a recursive query in a database? Common table expressions, connect by prior? Yeah, those are hands. You need a graph database.
It could help in some cases. So operational databases and the dimensions that you look at. So we kind of look at, OK, the size at limit. Is it bounded? Is it unbounded? If you really have data which is unbounded, you really should think about a system that can give you constant performance regardless of size. If you have a system of a database which the performance gets slower and slower the bigger it gets, and then you're not going to have constant performance. So that's a problem. If your data models best for key value, then use a key value store. If you're always operating on a record in its entirety, and record is a good thing, right? So these are some of the things that you should look at when you're going through this decision process. And we have to admit that this is not a simple thing. You go, OK, here's the 7 questions you answer. At the end of the day, you will know exactly which database to use for every workload. If it was that simple, then a lot of us wouldn't actually have a job. So let's talk about analytics. So this retrospective, predictive, and streaming thing, I think it's fairly, if you look at it historically, the retrospective analytics came first because people were able to then query transactional databases and see what happened in the past. Streaming analytics came in the way with the machine learning and people looking at telemetry coming from devices. And of course, the predictive stuff. If you don't think you need ML for your applications, well, you should really consider why is that you don't think you could benefit from that? A lot of workloads do. So on analytic workloads, almost always you're better off with some kind of a columnar format as opposed to not, because it is the most efficient. Why is a columnar format most efficient for analytics workloads? Because data in columns tends to repeat. Therefore, it's very compressible. As opposed to adjacent columns in a row are not related. Like my age is not related to my first name. Whereas the age of everyone in this room, I bet you, repeats a lot. There's probably a lot of people who are 37 years old. Yeah? No? No one?
But that's really easy to compress, right? No.
Yeah, there's only one. All right. They're usually large. Analytic workload require a lot of computational memory. Like when you're looking at 1 billion rows and you're computing stuff and you're doing joins and so on. Analytic workloads are rarely updated. It's an insert and it's a delete. Maybe it's a bring in a new partition, get rid of an old partition, but you don't go and change history very often. So there are a lot of in-memory capabilities for most analytic systems. And the things that you really have to then consider is that, do I have need to do streaming analytics? Do I need insight from a stream of data coming from somewhere? It could be devices. It could be, I don't know, maybe you're on a train system and you're emitting telemetry from the brakes and the temperature of the brakes from all the trains that are running in the city. And you need to know when the brakes on a particular train get too hot. And that's a real-time thing. So you need to analyze the stream of data all the time. That would be a streaming analytics. Do you do ETL? Do you move data back and forth? How much processing you do? Do you want serverless? Or do you need servers that are always there because, I don't know, you have a data warehouse which is being used 24 hours a day, every day? And then what is your data format? So these are some of the things that would help you guide. So we have Amazon Athena, which is one of our interactive analysis products. So when would I use Athena?
It's not a database, though, is it?
No, because I don't know what it is. Tell me, what is this thing?
Oh,
it's not a database.
Fantastic, because it allows you to treat data at rest, unstructured or structured data, like it was a database. And that's a really powerful concept. And we started this conversation around analytics with Athena because it is the place that you will probably start when you're working with your data. A very, very common pattern is that you're going to ingest your data into a format that is good for the type of data that you're storing. If you're working with lots of log files, then you're going to store those as log files, and you should compress those every time. If you're working with much more structured data, then using a format like Parquet or Orc is very useful because it implements that compression. But once you've written it down and it's sitting on a storage system, Athena just gives you the ability to start working with it. It's not a database, it's an engine for working with data, but it allows you to write SQL as though it was a database.
All right, so I'm a little confused. Let's say I have an OLTP system, and I do transactions, I sell stuff, and I have the last 5 years' worth of sales data, and I export it out of my OLTP system in a comma-separated file, and I put this file on S3. And I have done nothing else. You're saying I can query this file now with SQL?
That's right. So you're paying for the storage on S3 for the data that you should be keeping anyway, and then you're able to issue a query using ANSI SQL. There's no servers to provision. There's no babysitting of that environment over time. You simply pay for the data that streams through Athena, and you get your answer back. You can either use that in an interactive way with the Athena console, or you can use an API to save that data down to another location, whatever.
So why wouldn't I just take this export file and immediately import it into a columnar database and start querying it there?
Yeah, because, well, maybe you don't know what the shape of it is. Maybe you're integrating with a third party that has been known to add or remove columns from time to time. That's a really common use case that we see. In some cases, you will import data where you know the schema. And with the Glue data catalog and Glue crawlers, that data will be analyzed on S3 and lifted up into a format that Athena then can work with. Or you can work with data that has no format at all. We call it a model on read semantic. You apply a schema at the time you issue the query. And so you don't have to only work with data that you understand. And in fact, you might not actually know if it's useful.
Got it.
You may not want to import it until you know it's useful.
So if I get a giant data dump from some group in my company about every failure in the brand of cars that we make over the last 10 years, and this is like I don't know, a 15 terabyte pile of data, and I dump it in S3, you're saying I could start querying it to figure out what is in there, if there's interesting stuff in there.
That's right.
Before I actually start buying databases and provisioning stuff and loading it into.
Yeah, and that's why we say, it is really the first step on the journey of doing analytics. You should absolutely be investigating your data and doing data exploration to establish its value, to start to mark data sets as to their value, to enhance them potentially with other data sets so that you can really do that exploration process.
If I have a data warehouse and I have 10 years worth of data in there, but I usually just use the last, 2-3 years of data, can I take the old stuff and just dump them in S3, and it's there, I can query it anytime I need to, but then it will save me a lot of money because I'm not paying for databases that are running all the time to hold this data that I never use, but I'm not willing to throw away, and I need it to be queryable if somebody wants to.
Yep.
Cool. Well, that's pretty handy. All right, Redshift.
Yeah, so you just said if I had a data warehouse and I wanted to be able to issue queries, and then I wanted to do some cost optimization. So Redshift is really the counter side to where you're doing data exploration. With Redshift, you select Redshift because you understand your data, you understand its schema, and you understand its value, and you import that into a system that is designed for extremely fast query times at scale. And there's also the ability to integrate in an Athena model with Redshift Spectrum. So you don't actually have to choose either or. You can use Athena to establish that some data is actually useful. You can generate new data sets and immediately start querying those from inside of your enterprise data warehouse in a hybrid compute and storage model. So you get the best of both worlds of extremely fast query response times from data stored within the Redshift data warehouse, and then the ability to also use this data at rest on S3.
So this is because the data which is in Redshift has been consumed, converted from a bunch of text in a CSV into internal database formats as numbers and whatever, and it's been indexed.
That's right.
And now it's just queryable. You don't actually have to process the text or anything. You're just doing queries.
That's right. So you've probably modeled your data in a way that's sympathetic to the types of queries that you're going to get, as opposed to Athena, which is issuing a query that you can expect. And you might actually be modeling your data using a regular expression or a grok expression.
Right.
With Redshift, you know what that data is. You know that it has value to add, and you've done all the things that you described so that you can get that really, really fast query time.
So, it's very likely that the CFO always wants to know, we made the numbers, what was the numbers, what was the sales, what was the profits, and those are all well understood questions. The VP of sales always wants to know who are the top salespeople, did I make quota? Those are all pretty well, right? So if you're going to build a dashboard for people to look at these reports, and you want the dashboard to be really fast and people don't wait more than a second, then you want the data to be in a database which is already processed and indexed, so for fast queries, as opposed to something like Athena, where you say, okay, go open this terabyte of stuff and figure out what the schema is and do some conversions, and when I say do a sum, then you go read all of that stuff. It might take longer, but then, of course, you didn't pay for unused servers to sit there for days and days and days.
That's right.
Okay. So streaming.
So both of Athena and Redshift are about doing retrospective analysis of data that you've imported into an environment. You've written it down. You've said, I want to keep this, and I want to be able to establish trends, and I want to be able to train models that then take those retrospective measures and predict them in the future. Kinesis Analytics is about the now. It's about the ability to do analytics second by second by second as the data comes in. And again, the common thread that runs across these analytics tools is that they use SQL. Athena is using ANSI SQL. Redshift uses SQL, ANSI SQL. And Kinesis Analytics uses streaming SQL. So it's really all about moving historical analysis into that very, very short term of decision making. And you need to have an answer very quickly, and your business needs to be able to react to that. There needs to be business value associated with you making a decision quickly. So an example would be a customer support case where you have an unhappy customer. The sooner you know about that, the sooner that you can react to it, the sooner that you can understand maybe that consumer's device is failing, you can then proactively address their issue and make sure that they have a good outcome. And the faster you do that, the better off you are.
Or the telemetry coming from the trains when the train is going up the hills, but the brakes are hot, and there's no reason for the brakes to be hot while you're going up the hill.
Exactly.
Because when you start going down the hill, something bad's going to happen, and you want to know that and raise an alarm before.
Yeah.
Right. You don't have time to index that data into a data warehouse and query it later.
That's right. That's right. So in the case of making a decision in the now, making a decision retrospectively, we've been doing a lot with SQL.
Right.
There are other cases of where you want to be much more flexible about how you can ask a question of your data.
Okay. So tell me why Elasticsearch even comes up as a database here.
Yeah. Well, it does store your data in the form of specialized indices for doing a specific type of query. So you might have an index that's particularly good at doing a natural language search. You might have another type of index that's really good at doing a time series expansion or interpolation. You might have another type of index that's particularly good at doing geospatial manipulations. And so in these cases, you want to do analysis that isn't about select star from whatever. It's about having a lot more flexibility to explore your data in different ways that are probably more natural for, again, that exploratory case. And certainly with the case of Elasticsearch, given that it has Kibana bundled in, you have the ability then to create graphs and dashboards that are based upon these much more interesting types of queries and much more powerful for certain types of problems.
Right. So if I was storing documents in, say, Dynamo, and I have, I don't know, big giant JSONs, there's free text, you told me that the update stream from Dynamo can actually send the changes that are happening, and I can have a Lambda trigger that calls Elasticsearch and indexes the data in Dynamo, so that my application can go query Elasticsearch for a particular keyword and find all the records in Dynamo?
Right, exactly.
See?
Exactly. Or to apply a time series expansion on a stream of IoT data that you're storing in DynamoDB, because it's extremely high throughput rates, and you need to be able to find anomalies, for example.
All right. So the things that matter in picking the right database for analytics: is it streaming or not? Is it serverless ad hoc queries? Do you find value in that? The process, prepare and index in place or not, pay per query, or do you have dedicated servers that you pay all the time? So these are all the interesting things. Now, the last line here, just spend a few seconds on, if you have data sitting in S3, which happens to be a CSV, you query with Athena, of course you have to convert the text into numbers and stuff because you want to do sums, so that you pay the computation, that brute force computation, you pay that while you're querying. But something like Athena can also open other formats like JSON and Parquet. And Parquet is a columnar format, which is very handy. So if you actually store your data in the format of Parquet in S3, when you run Athena on it, then you don't have to do the conversion, pay for that at the query time, because you're already converted the data and you can query. So there's a lot of interesting combinations that you can get to with these workloads. And one of the things that's very obvious to us when we look at very large customers, I have yet to find someone who says, no, we have one data warehouse, it's one kind of a database, that's all we need, we get all the insights from that thing, and that's it, right? Not these days, where people are trying to find insights from all kinds of data. So what we do see is a lot of people who have a hybrid systems. You might have Redshift, you might have Athena, you might be doing streaming, you might have your operational databases wired to your analytics systems. You might be going through S3, maybe your operational databases occasionally export and dump stuff in S3, which then you can query with Athena to see if there's anything useful in there, which then, if you do find it, you might actually write an ETL job to go from your OLTP system directly to your data warehouse. And the nice thing about these combinations is that you basically start using the right set of tools, right? Because maybe you don't need to have servers that are up all the time, because you occasionally query some data, and that Athena comes in really well. But for the dashboard that you need to be active all the time, you use Redshift, or you use a combination of all of them, which really brings back to the portfolio. Choosing the right database, it's not about choosing the right database for everything you do. It is choosing the right set of databases to apply to the right set of data for the particular applications that you have. And I think you'll end up using a combination. And this is why we kind of are pushing for the managed stuff, because if you're going to use a combination of databases, you certainly don't want to have to figure out how to do backups on DynamoDB and Aurora and Redshift, because that's really painful. So we do that for you, so you don't have to deal with the manageability part. So this is kind of the stack. If you look at the stack, how do you move data? Where is the terminal place for data? Something like Glue, where you can do your ETL. You have your operational databases. You have your analytics databases. And then you have things like QuickSights that sit on top for visualization, dashboarding, and your reports and such. And then we announced SageMaker, which is basically our machine learning capabilities that you can now use to apply to your analytics workloads to even build models, and maybe you even start using some of your models in your operational databases. So, I don't know, for scheduling staff at the restaurant on busy days. So this is kind of the picture that we're driving. Again, purpose-built databases are more efficient at scale. So if you're building big stuff, don't try to stuff everything into the one database because you think that's more convenient to just have one. I think the diversified backends for databases ultimately end up being better. We try to make sure that everything is managed so you don't have to take the inconvenience. And we are always trying to stay open. So Elastic Cache, for example, with Redis or Postgres or MySQL, none of these are AWS thing. You want to take your MySQL database somewhere else, you can. And so that is the idea of remaining open so that you can bring stuff in and you can take stuff out. You want to bring your MySQL or SQL Server or Oracle or take it out. That openness allows you to do that. And of course, the customer obsession is, you tell us what doesn't work for you, give us feedback at reInvent. We go spend the next 12 months fixing all the stuff that you want us to fix. We come back here, and then we start the cycle all over again. So I'll pause here. Maybe we have 4 minutes, so we'll take a couple of questions. If you have any questions, please use the mic so people can hear your question.
You had mentioned DAX. DAX, and in the case where you're using DAX, is there any need to use Elasticache, and especially if you're wanting to run geospatial queries?
Sure. So DAX is really then going to give you the ability to query through to DynamoDB. If you have other types of queries you need against other data sources, and you mentioned geospatial, for example, then you may run that query against a Postgres database and then push the geospatial coordinates, for example, into a cache so that you can consume those over time. So pick up my most recent route, or route options, for example. If you were doing a mapping application, you might say, go compute a few routes, cache those, so if somebody wants to come along because there's now traffic works, then they can pick those out, for example.
You could also use Elasticsearch for that and then put a cache in front of that for the geospatial types.
Thank you.
Yes?
Where do you see a data lake sitting in all this?
Sure. So data lake really is going to be the foundation of data at rest for all of the different types of data that you're ingesting, and give you the ability to make these choices about which engine to choose for a particular problem. So we start to see that data lake is the foundation of data storage, and then you start to look at projecting that data lake data into an engine to solve a problem. And so I think they work very well in concert, and the data lake gives you the ability to change over time to take advantage of new technologies as they come about. And a great example is Neptune. If you have a query that you're servicing today with a relational database, you have the ability to push that through your data lake and load into Neptune and start using an A* query, for example.
Okay.
Yes?
What is the difference between Athena and Redshift Spectrum, or what is the use case for each one? When do you use it? Okay.
Yeah, great question. Comes up very, very frequently. So Redshift Spectrum is for data that is optimized for working within like a star schema model, for example, because it is a data warehousing workload, and Spectrum is the ability to separate compute from storage within an enterprise data warehouse architecture. Athena is very different in that you're applying a schema either through the data catalog or when you're actually issuing the query. And so you have a lot more flexibility in terms of the types of data that you can issue queries against with an engine like Athena, whereas Spectrum is for giving you very well-structured, well-modeled data where you're getting the price point of S3 because probably that data is not as high a value. And in fact, you can share data between clusters using Spectrum, and you can query the same data that you're querying from Spectrum in Athena and vice versa. So you don't only have to make one choice versus the other, but certainly the source of data for Spectrum tends to be well-modeled data warehousing type data.
You also have to have a provisioned Redshift cluster to use Spectrum,
True.
because that's where the compute
So
comes
can
from.
we assume that the structured data, instead of loading into Redshift, keep it in S3 and then use the Spectrum for querying it?
Yeah, absolutely. Yeah. You know, it's a very common pattern where in order to keep the, we talked about the hot working set for an operational database. Well, analytics has the same thing. You may say, we really only tend to query a year's worth of data, so you keep that in your data warehouse. You keep everything forever in Spectrum, and then you only need to size your Redshift cluster to deal with the hot data. You can still reach through into the data store we're using Spectrum.
Thank you.
Yes, on the left side.
What do you say about Cassandra? Is there any recommendation of shifting to one of the Amazon supported stuff, or?
So Of course, DynamoDB is a good place for that, especially now that we have global tables that we announced today, where you can have replication across regions, you can do master-master, and a lot of people use Cassandra for that. And lots of people use Cassandra in EC2, and one of the reasons a lot of customers that we see that move from Cassandra to Dynamo is because they just don't want to manage the Cassandra cluster. Otherwise, you have the option of running Cassandra in EC2 or use DynamoDB. That would be the place to go.
And it's also important to call out that DynamoDB is quite unique in that it supports both a document-oriented interface for working with data, as well as something that's more like a column family database like Cassandra. You kind of get both in this which API you use.
Yes?
Actually, following up on the document database part of Dynamo, one of the use cases we have is we have JSON stores or XML stores, which we'd like to store and be able to query those by different attributes. Is that possible with Dynamo now?
You have the option of using the global indexes and local indexes, so you would be able to index on a property for that.
But could we do all the properties to be auto-indexed?
We don't have an auto index for all properties. And you have to take care about just indexing everything all the time, because it has consequences, right? Things get big, you have to pay for it. So we would recommend that instead of auto-indexing everything, to index the things that you really need. And then if you really want to, you can also do the Elasticsearch to index some of the things which you think needs an indexing in a different way than the indexes that Dynamo provides. And using the Dynamo streams to then send updates to Elasticsearch is a really good way to go.
Thank you.
Yes, last question.
So our team has started exploring into predictive analytics for strategic planning. How they do currently is get a data dump in CSV formats, but these are multiple spreadsheets, and they manually kind of do VLOOKUP on spreadsheets and combine into one. So how can Athena help me in combining these spreadsheets? Do I have to do it manually and dump it into, put it on S3 so that I can query the data that I want? Or do I have to use some kind of Lambda to kind of combine these spreadsheets and then use Athena over it?
Sure.
Go ahead.
Yeah, so there's a lot of different options for how you would mix that data together and enhance it, and certainly the ability to import CSVs via your data catalog and then issue queries that would mix that data together. You don't necessarily need to go at that problem with an ETL-like approach. You may be able to query it at rest, combine it, enhance it, and then write a more structured, modeled set of data that meets some business needs. So yeah, very common use case. It's also worth mentioning if the CSVs are useful in their own right, those can be imported straight into QuickSight, and you can just start using them.
Okay. Thank you.
All right, so we're out of time. I'll be hanging around here if you just want to come and chat for a little while.
Thank you.
Thank you.